Okay, okay, now we are live. Okay, the next speaker is Fábio Ramos from Instituto of Mathematics, but it's Universidad Federal of Rio de Janeiro. He's going to talk about similarity of turbulent pipe on channel flows at extreme Reynolds number. Okay.
All right, thank you, Gabriela. Thanks for the kind invitation. So this is I'm going to talk about this two works in collaboration with professors Barlouet and Cruz from the Federal University, and with the PhD student Gabriel Sanfins. This is a recent work. So I'll start with the similarity, right, to understand what I'm talking about. So the most common similarity parameter that people use to work with in fluids is the Reynolds number, is the number that allows you to scale up from prototypes to the real thing, right? And of course, as mathematicians, you know that you can normalize the Navier-Stokes equation in such a way that you could have here so in the dimensionless variables, like quantities, the 1 over Reynolds shows up here. And it's natural to believe that when Reynolds is really, really high, then the effects of the Laplacian here, the diffusive effects, is small, right? And then you'd approach something similar to Euler, right? Something more inertial than diffusive. But that's elusive, because if you're working with the incompressible flows, you know that you have non-local behaviors. And especially if you are in the presence of boundaries and you're working with the more used boundary condition, the no-slip boundary condition, u equals 0, you know that you cannot really ignore this effect, right? So this is a picture from a simulation of Lee and Moser and Malaya. And it shows, right, that the velocity profile, so that the colors are related to the velocity profile intensity and velocity fluctuations. And you see that near the wall, the physical behavior is very different than the core region. And this kind of thing is the reason that you cannot really ignore, right? Cannot take the limit straight. You have to be very careful. The Reynolds number, as you know, it's the control parameter of turbulence. For a small Reynolds number, you have some laminar flows, and then you increase the Reynolds number, you see some transition. The transition can be seen through this structure changes, right? And then you have this transition to turbulence. And people used to think of two types of flow, laminar and turbulent. And that's it. Once you reach turbulence, you kind of have the turbulence world, and it's one single world, and you have to just deal with that world, right? So here just some orders of magnitudes. A whale at 10 meters per second is 300 million Reynolds. Duck flying is 300,000. The human swim is 10,000. It's good to have this order of magnitude, right? So we are used to work either with the laminar flow or the turbulent flow, and have these two words. But what I'm showing here today is that actually you should consider three worlds at least, right? So this is a work published last year, The Physics of Fluids. So we show that for a small Reynolds number, the friction factor, I will define everything here today, is it scales with 1 over Reynolds, and the wall shear stress scales with mu, u bar, which is the bulk velocity, over delta. Delta is the radius of the pipe. And this wall shear stress yields this friction factor, right? And then you have some transition to turbulence, and then the wall shear stress scales with rho u bulk, u eta, and this u eta is Kolmogorov velocity. And then the friction can be written as this ratio of Kolmogorov velocity to the bulk velocity, and this gives the Blasius range, the one of Reynolds 1/4. And then people usually thought of Blasius range as some empirical correlation, not very physical or mathematical. And but recently we learned that you have some physics behind this scaling, right? And then there's some crisis here, some other transition, some late transition, and then you have this transition to another scaling where the wall shear stress scale with this rho, U bulk, and UM, where UM is the mesolayer velocity. So since we are among among mathematicians, I think it's nice for you. I mean, these are more physics talk, but I know there's some interesting things here that could be useful for a more mathematical audience. So I'll try to focus here. And then this wall shear stress then scale with a different velocity, and the friction factor now is the ratio of these two guys. And this case with the one over Reynolds 213, and it goes really well. So this is very new. It's from last year. And the other result is some more corroboration that this is true, that you have a secondary transition to turbulence. So when Reynolds is very, very large, we will show that there is a transition, that the mean velocity profile collapses into one singular self-similar profile, right? When you scale with the bulk coordinates. And this will be related to some incomplete similarity notion, which is not very discussed in the Western literature, but the Russians know very well. And then you can move to the usual wall scaling of the mean velocity profile. I'll define everything here, right? Okay, so I'll start advertising this very nice book by Baron Blah, The Scaling, right? And so much of the concepts I will discuss here, not in the context of fluids, it's there. There's some in the fluids also there. So I'll start with the Buckham's pi theorem. So if you have a physical quantity of interest, A, and some governing parameters, such that the A is a function of these parameters, you have n parameters, but you divide these parameters such that the A's have independent dimensions, right? Dimensions like mass, time, mass over length, stuff like that. But the B's, they have dependent dimensions. The dimensions of B can be expressed as products of powers of the dimensions of A, as well as the quantity of interest itself. So the A's, the A1 to A is the independent, they have independent dimensions, right? So what the Buckham's pi theorem says is that if you have a physical relationship like this, you can normalize these variables. The A, you can normalize, the B's, you can also normalize them, such that you have these dimensionless parameters, and you have some generalized homogeneity property, right? This is modeling 101, right? So you can always write this physical F like that, as you take the A's out, and you have only the dimensionless parameters inside the phi, and then you can rewrite the physical law in dimensionless variables, right? So this is the pi theorem. You can always write a physical law in a dimensionless form, right? Which is obvious, right? So this is Buckham's pi theorem. The Buckham's pi theorem yields some similarity group of transformations such that you are free to multiply the independent parameters by positive numbers, A's, capital A's. And if you change accordingly the dependent parameters and the physical quantity of interest, then the generalized homogeneity still holds. So you have this invariance through this K parameter group, right? So you're free to choose units, right, if you change things accordingly. Let's go to the friction factor of fluids. So you have a flow flowing through a pipe, and I'm considering that I'm far from the inlet and the outlet, and this is statistically stationary, and this flow is driven by a pressure drop. The pressure here is higher than here. So the dimensions of pressure drop are like this. This is mass, this is length, this is time, right? The bulk velocity like this, pipe diameter, density, dynamic viscosity. You can rewrite the dimensions of the pressure gradient like this, so that you can form a dimensionless parameter like that. The dimensions of mu can be written like this, so that by the Buckham-Pi theorem, the pressure gradient, using the generalized homogeneity, you can take out these guys and have just a function of this dimensionless parameter. And this dimensionless parameter is actually 1 over Reynolds, right? So this is Reynolds showing up here. This is the Reynolds number. So if you write this dimensionless quantity called the friction factor, we know that this friction factor is a function of Reynolds. The friction factor is the single most important quantity in engineering applications in fluid mechanics. That's what determines the design of piping systems in several applications, right? So it's really, really important to understand the friction factor for different flows. So, because it's very important, people know a lot about that, right? This tau W here shows up here. This is the wall shear stress. I will show now how it appears here in the friction factor formulation. So let's assume you have like now a channel flow, right, driven by pressure gradient. You have a constant pressure gradient if you have statistical stationary solutions. And then this is the total shear stress. This is the viscous stress. This is the Reynolds stress. In the fluid mechanics literature, people work a lot here with this stresses. But what is really important for our work here is to consider the full second law of Newton, right? Newtonian mechanics. So you're not dealing with the stress itself, but with the gradients of stress. So when you write this, so this is the axial mean moment equation. This is valid all over the channel. And this has dimensions of force. So this is balance of force. So this is the viscous force. So the force that comes from viscous imbalances, from diffusive imbalance. This is the force generated by Reynolds stress imbalance. And these forces are balanced by the pressure gradient force, right? If you integrate, then you know that the total shear stress at y is the distance from the wall, the bottom wall. This is y, right? So the total stress at some distance y from the wall has this linear relationship, and this coefficient here is the wall shear stress. Is the shear stress here at the wall. At the wall, this is 0. So it's just the viscous stress at the wall. And then using this relationship here, you can prove easily that the pressure gradient is actually the wall shear stress over delta. So that's the relationship between pressure gradient and wall shear stress. So to define a pipe flow driven by a pressure gradient, you have to define either the pressure gradient itself or the wall shear stress. That's enough. One replace the other. So that's why you have that the friction factor can be written like this with the pressure gradient or the wall shear stress. That's the definition of friction factor. And already in 1911, Blasius assumed some special power law form for the mean velocity profile. And he showed by experiments that this friction factor scales like this, right? 1 over Reynolds, 1/4. But after some range, after 10 to the power 5, Blasius correlation is not valid anymore, right? So there's a limit for this law. And people always thought that the Blasius correlation is more like empirical correlation with no physics behind it, right? In the 30s, right, 19 years, 20 years after Blasius, Nicorazzi did main experiments with smooth pipes, right, and showing that really Blasius is no longer valid after 10 to the power 5, right? But he also did many experiments with the rough pipes. And depending on the roughness element size, the friction factor follows Blasius, but then there's a crisis, and then the friction factor goes to some constant, right? So when people discuss singular limits in fluid mechanics, you know, a place where people really should look at is rough pipes. You do have this constant friction. Something happens that becomes constant. Okay, so this is all about friction factor. Let's take a look here, some visualization of the turbulent channel flow by these guys from KAIST, from Korea, right? This is really nice simulation. This is not very high Reynolds number. It's still in the Blasius range, right? And the velocity, the colors are normalized by the center line velocity. So you see that it's very fast here in the center line. Near the wall, this blue showing that is very slow, the velocity field. Of course, it's U equals 0, the boundary. And then there's a transition layer, right? This green area, right? Take a look here at 0.25, halfway, right? It seems that, you know, some guys come from up and go down, down from the bottom, go up. You see some circulations here. You see some vortex, right? So this is the usual thing that when you think about pipe flows, channel flows, you have this core region, you have the wall region, you have some intermediate range region. That's how people usually think of this pipe flows. So you have this different domains of the flow. So let's take a look at scaling of the mean velocity profile. So the mean velocity profile UI is actually dependent on the pipe radius or half of the channel height, the density, the viscosity, and this quantity that I call this delta nu, right? This delta nu is mu over rho over u tau, and u tau, this is the wall viscous length scale. This is the length scale that you should use in your rule to see things near the wall. And this u tau is the friction velocity, and you can form it with the wall shear stress, the square root of wall shear stress and rho. And remember, wall shear stress and pressure drop, they go hand by hand. So if you have pressure drop, you have wall shear stress, and then you have u tau, and you have delta nu. So I just could put here pressure gradient, I could put here u tau, I could put here delta nu. I decided to put delta nu because it will be very important, right? So this idea comes from Brunto more than 100 years ago. So he said, well, let's normalize the distance from the wall with delta nu. Let's look at using this wall unit delta nu, this is the y plus, and the velocity you should scale with u tau, the friction velocity. So these are the inner coordinates, the wall coordinates that you should, you know, the truth should reveal itself by looking with these glasses, right? This is what Brento thought. So this is the semi-log plot of u plus against y plus, and then you see there's a linear region here. In the log, the linear looks funny, but it's a linear region here. This u plus equals y plus. That's by definition of these coordinates. And then there's a region where there's a log law, some intermediate region that people call the log law region, right? People already knew that you have some wall region, intermediate region, some core region, so that was natural. But the log law comes. This comes earlier, and then this u plus is a function of y plus. But by the Buckham's pi theorem, you have the right to use another dimensionless parameter, pi 2, right? And it's open to discussion. So the mean velocity profile scaling, you have to look, let's look at in two worlds, the inner world close to the wall and the bulk region, right? Far from the wall, near the center line. So you should scale in the inner region with y, delta, rho, mu, and delta nu. And in the bulk region, you should actually use the bulk velocity itself. Why not? This is the average. This is funky because these depend on this, but you know, everything is coupled here anyway. And you have different control parameters. To have a separation between the inner region and the bulk region, it's relevant to consider this friction Reynolds number. So this is delta over delta nu. This is the pipe radius over the viscous length scale, the length scale near the wall. So if this ratio is really, really large, you can expect a separation of a center line world and a wall world, right? So if this Reynolds style, this friction Reynolds is very large, you do expect some separation, some intermediate region, right? By Buckham's pi theorem, you can rewrite this with the U tau. Remember, U tau is some combination of mu, rho, right? And tau w and delta nu, right? So the U tau goes out, and then you have these two control parameters. You could also write like this, y over delta nu, and here y over delta. This is another dimensionless parameter. It could write like that. The bulk, if in the bulk region, the natural way of writing this is to take the U bar out and have this dimensionless parameter and the Reynolds parameter. You can form Reynolds here, but you cannot form Reynolds tau. You cannot form friction from these quantities. And the way to relate to the bulk with the inner world is really through friction factor. The friction factor actually, when you define it, you can see that the friction is actually some constant times U tau square over U bulk square. So this U tau and U bulk, they are related to each other through friction, right? And the Reynolds tau and Reynolds, they are also related through friction. So friction is really important to going through from the inner world to the bulk world. Remind that for laminar flows, you have a parabolic law, and for turbulent flows, you have a more flatter region here, right? For rough pipes, the thing can be also really flat, right? Even with a smaller Reynolds number. Anyways, these laws depend on where you are in the pipe, right? So if you're near the wall, you have one law, you expect one law. If you're in the intermediate range, you expect another law. If you're in the bulk range, you expect another law. So this is not a universal profile for all the pipe, right? You have to understand that. And for rough walls, it's even worse because then you have to consider the roughness scaling as well. In terms of the similarity groups, when you rewrite this thing using the Buckham's pi theorem like that, this is actually equivalent to saying that you have this K parameter group of transformation in such a way that if you are free to choose positive constants here and change the viscosity, the density, and the delta nu. The dependent variables, you are stuck. You have to use the same A3 here. And the quantity of interest, which is the mean velocity profile, you have to change like that. And then you obtain a three parameter group invariance. So if you change like this, you have the same law, right? So it's good to have in mind that a pi theorem formulation is related to some K parameter group symmetry. Okay, the log law in the 1930s. So Pruntel and von Karman realized that if you, this argument is by Landau, but let's use it. So if you write the gradients of velocity and you scale with U tau and Y, right, and then you have a phi. This is the Buckham's pi theorem for the gradients of velocity, or the mean velocity profile. And if you write like this, and then if your Reynolds tau is really large, so that delta over delta is much larger than delta nu, then you have an extensive range where Y is much larger than delta nu, much smaller than delta, right? And then you expect some sort of complete similarity. I will talk about this soon. So in this range, these things become constant, this phi. So this constant is 1 over K, this K what people call the von Karman constant. And then if you integrate, you get the log law. So that's a very cheap argument to get a log law. And then you see here, this is from experience from the Cyclop. And then you see some log law region. There's some dispute concerning the K. There's lots of variation depending on where you fit and B itself. If you use the log law and you manipulate here the U-bulk and the friction factor from the mean velocity profile, you get a friction factor which has this logarithmic ugly face, which works very well. This is very well. So this is data from the Princeton super pipe, and it does the work very well, right? Okay, so this is what people understand classically about pipe flows. But in 2006, Joy and Chakraborty, now in Okinawa, they realized that they proposed a wall shear stress closure, saying that, well, okay, maybe let's close the wall shear stress that's related to the Reynolds stress in some wet layer, and this is related to momentum exchange with the horizontal fluctuation is bulk velocity, and the vertical fluctuation is Kolmogorov. So if you put this scaling here, the friction factor, this becomes the friction factor becomes proportional to U Kolmogorov of U bulk, and you use the K41 scaling, and this is actually 1 over Reynolds 1/4. Okay, and then people believe that, okay, maybe this is just a coincidence, but my coworkers and myself, we published some series of papers in non-Newtonian fluid flows. Oh, I put non-Newtonian, so it's Newtonian. It's non-Newtonian fluid flows. For an extensive family of non-Newtonian fluid flows, you obtain several friction factor formulas for many non-Newtonian fluid flows using the same rationale. We just change the Kolmogorov velocity depending on the rheology. So it seems that this is true. This scaling works. There's some physics behind it. But for some reason, after some range, Blasius doesn't work anymore, and this scaling doesn't work anymore. Something changed for very high Reynolds number. And this is our work last year. So it starts with the concept of mesolayer, right? The mesolayer concept is a little confusing, but let's go there. So if you have the Newton's second law here, balance of forces, viscous forces, turbulent forces, and pressure gradient forces. If you normalize it by U tau square, right, you can rewrite this. The pressure gradient, the minus pressure gradient becomes 1 over Reynolds tau. The viscous term becomes this, and the turbulent term becomes this, right? This means that we are normalized by the wall units, right? At the peak of the Reynolds stress, if you believe that the log law is still valid at the peak of the Reynolds stress, then this thing here, we know the second derivative is 1 over y squared, right? The derivative of log is 1 over y and minus 1 over y squared. So this becomes 1 over y squared. At the peak, this is 0. So at the peak of Reynolds stress, if the log law is valid there, then the location of the peak of Reynolds stress should be Reynolds tau half. We believe that our argument was like new, but we know that then we found out that this is very well known. And actually people get this relationship even without assuming the log law at the peak. So there are many, many works discussing the peak of the Reynolds stress. But what's really important is that if you look at the ratio of viscous force to turbulent force, this ratio is kind of, viscous force very important near the wall, balance the turbulent force almost up to the peak of the Reynolds stress. And then after this region, this third region here, then the viscous effects become very small. So somehow, this is by paper by Vey and all, JFM, Journal of Fluid Mechanics. So somehow the effect of viscous force persists up to Reynolds tau half in these Y plus units. This is very different from the usual log law rationale. People believe that the viscous effect should stop at Y plus equals 100, 150, 300, some fixed number. But no, we are saying that actually it's Reynolds tau dependent, right? So this is the region, this layer, this mesolayer, is where the peak of Reynolds stress is where you have lots of momentum exchange between the wall region and the bulk region, right? This is the mesoscaling, this y plus equals Reynolds tau half. If you write in the normal units, right, multiplied by delta nu in both sides, actually this thing is the geometric mean of delta and delta nu. So you're saying that at the geometric mean of delta and delta nu, which is invariant, right, you have this very special place where you have lots of momentum exchanges, the peak of Reynolds stress. And then we go through some mumbo jumbo arguments using some touch and eddy hypothesis. But what's important here is that if you assume that the wall shear stress has this momentum exchange scaling, right, from this fast part and this slow part, and here this u of y minus s, this is essentially zero, is very small. The velocity here is essentially scaling with a u bulk, and this Vm is some velocity fluctuations in the vertical direction, right? So if we assume this, right, then we can derive this expression for the friction. You put this, and then you have Vm over u, and then here I'm using some Kolmogorov K41 similarity. So somehow Vm scales as epsilon m 1/3 Lm 1/3, right? So you have this K41 similarity. I just divide by delta nu in both sides. Remember, this is 1 over Reynolds tau half, this location of the peak of Reynolds stress. So it's 1 over Reynolds tau half, then becomes 1 over Reynolds tau 1/6. And then using this relationship between Reynolds tau and Reynolds through friction, you obtain the 1 over Reynolds 213. So that's the argument, that's the scaling argument. And then when we check with the Princeton superpipe data, boom, we got there. You really have this 213, this is less than 1% error, right? And then you have some new transition. So this is the paper from last year. The arguments you can find in the physical fluids. And then we went through some investigation of the mean velocity profile. So, okay, but what does it, what this transition means for the mean velocity profile? I don't have much more time. I just want to have this takeaway message before we go to the details, is that if you normalize the mean velocity profile by U bulk, right, the average of the velocity, and send Reynolds to infinity, these mean velocity profile, all this mean velocity profile converge to one single profile when you normalize in this U bulk. This is eta is y over delta, y over the radius, right? So you have some asymptotic, some singular limit at the when Reynolds goes to infinity. So that's why I think maybe it's important for you guys that work with implicit limit, you know, this kind of stuff. When you have pipes, you should understand that you have an asymptotic mean velocity profile. This is kind of trivial to plot, but somehow people, I mean, it went unnoticed by the community, right? So you do have this transition to the super turbulence regime, right? Okay, so let's talk a little about complete similarity and complete similarity. So the Buckham's pi theorems, you say that you can divide, right? This comes from the dependent parameters, the independent parameters, dependent parameters. This is already normalized. And then it's common to consider that some of these parameters are very small or very large. And in the limit of very small or very large parameters, you can just consider the non-asymptotic parameters, right? When this happens, when you can ignore, for example, you set Reynolds to infinity and you can ignore Reynolds, then we say that you have complete similarity in the remaining variables. That's the notion of complete similarity. This is usually rare in physics. What you have more frequently is the notion of incomplete similarity, is that you cannot just ignore this guy, but you can renormalize. You can kind of just use the pi 1 to pi L, but you have to normalize by the remaining parameters and take out these remaining parameters here. So you have to normalize in its own normalized variable. That's why I call this renormalized parameters, right? This When this happens, we call it incomplete similarities in the remaining parameters, right? And this is related to some renormalization group. I don't have much time, but essentially saying that you have an additional group of invariance. You can, the independent parameters remain the same, and then you can play a little bit with some of the dependent parameters, right? So you have an additional invariance group, right? And we call this the renormalization group. So let's work with the laminar flows. For laminar flows, you have in channel flows, right, with half width like delta. This is the solution, it's a parabola. And if you write the delta M like this is the mesolayer length, you can rewrite this laminar Poisson flow like this. This is the y plus, but you cannot write just as a function of y plus. The mesolayer length appears naturally. Remember, these are constant coefficients. So this is very natural to use the mesolayer, right? And then you can relate the y over delta M to y plus through Reynolds tau. There's a relationship through Buckas-Pi theorem. That's easy. And then you can define some phi function that depends on y plus a Reynolds tau, right? I'm just rewriting these things here in a funny way because I want to write the incomplete similarity relationship for the Poisson flow. So the parabolic Poisson flow can be written like this, right? Either with these natural parameters, or if you insist with y plus the Reynolds tau, then you have this mixed polynomial, right? You have the Reynolds tau and y plus multiplied. And then if you define this other function, it doesn't matter much, it's just because I want to write this. This phi function, which appears here in the Poisson flow, can be written this incomplete similarity way. This is a dimensionless parameter, this is a dimensionless parameter. So I'm renormalizing things. So the Poisson flow can be written in a renormalized version, right? In an incomplete similarity version like this. So you do not have similarity in U plus Y plus with a Poisson flow, for Poisson flow. But if you renormalize it, then you have similarity. So that works for laminar flows. So you have these relationships for Poisson. Now, through friction for Poisson depends on Reynolds tau minus 2. You have this relationship for friction, and then the bulk velocity is Reynolds tau U tau. And you see here this Reynolds tau, then it's actually U bulk in disguise. Actually, for Poisson flows, you know that U bulk is 3 times U tau Reynolds tau. So this thing here, you could rewrite this with U bulk. And if you use eta as y over delta, right, then you can rewrite the solution of Poisson flow in bulk coordinates like this. You have complete similarity for the Poisson flow in bulk coordinates. So if you plot in y plus versus U plus versus y plus, you don't have similarity for Poisson flow. But if you write in the bulk coordinates or in the renormalized coordinates, you have one single profile. So it seems that you should be using this renormalized version or the bulk version to see the Poisson flow, and it's related to some renormalization group of invariance. I don't have much time. So what we've seen that if we use these bulk coordinates, you have complete similarity, and by using friction, you can relate this to some incomplete similarity. And if you multiply both sides by Reynolds tau gamma over 2, then you get U plus and Y plus. So if we use this relationship, you go from bulk coordinates, complete similarity to incomplete similarity to this U plus against Y plus. So these are all connected through friction relationships. Details can be found in the paper. So for laminar flow, the friction is 2. And for the extreme Reynolds, what happens if I put the scaling of the friction here? If I put the minus 1/6 here, what happens? So that's what it did. So you plot in bulk coordinates, and you do see complete similarity in bulk coordinates for the extreme Reynolds range. And that's funny that here in 0.25, U equals U bulk for essentially every Reynolds high enough. That's weird. I don't know why it happens. And then for eta larger than 0.25, you have the decreasing sequence, and here you have an increasing sequence. I will plot this in a different way. So this is the Reynolds, right? And this is U over U bulk, depending on several values of eta. So 0.25, U equals U bulk. It's like one. It's weird. And then you have this increasing and this decreasing dependence below or above the 0.25. And then you do have the renormalized asymptotics as well, right? Well, I don't have much time. I just want to say that, okay, we went a step further and say, okay, but what it means for the U plus against Y plus coordinate that the engineers are used to use. So for Poiseuille flow, you have this this polynomial, right? This was a parabola. We are trying to extend this idea. Instead of using a parabola, you have a polynomial, right? But what polynomial is this? So we proved that if you want incomplete similarity, like this, Reynolds tau alpha, Reynolds tau beta, you don't have much choice. This coefficient should be the coefficients that come from the friction, and this beta equals 1. But when you put beta equals 1, this is 1 over delta, this is eta. So in other words, if you want incomplete similarity you have to use the 1 over 12 here, and here it has to be 1 over delta, y over delta, right? And then we have to search for values of lambda, which is what is lambda 1, right? So so I'm looking for this lambda 1 for some proposal of polynomials, right? So if I rewrite this thing like this, and I want to use the delta nu here, the only way that I can do this is choosing lambda 1 equals 1 over 12 here. And if I want to use, and this delta C, I'm free to find, I'm free to choose. If I want to use here the mesolayer scaling, believe me, the only choice is 1/6. So summing up, we propose some mean velocity profile fitting strategy using this 112, 1/6, and it works fine for the book velocity. The errors are very small, they converge to 0. And that's the same for the incomplete similarity, right? So you have some power law for this incomplete similarity. It's nice fitting as well. But why are we doing this? Because we want to multiply both sides by Reynolds tau over 1 over 12. Then you get U plus here against Y plus. So when you multiply by Reynolds tau 1 over 12, this is U plus and this is Y plus, but you have to pay some taxes here with the Reynolds tau. So people are searching for Reynolds tau independent power law formulas, but that's not possible. Parambla had somehow argued in these lines. So this U plus against Y plus, we propose to use this formula, and then it fits very well. We compare it with the log law from Pruntel. So this is the errors from log law. This is the errors from our formula. The errors are good, are smaller in some regions. So our formula works. So in summary, because we have very large experimental data for turbulent pipe flows, we were able to see that you have some secondary transition to turbulence. We have some phenomenology using linking the mesoscale with the new friction factor. It seems that the mean velocity profile has some sort of singular limit, some complete similarity in bulk coordinates. We linked this complete similarity to incomplete similarity, and you use this incomplete similarity to propose some polynomial models in the classical inner coordinates. So this, I know it was a lot, but I mean, if you want to hear more about this, just send me an email. That's it. Thank you. Thank you.
Thank you very much for the nice talk, Fábio. Are there any questions, comments? Anna, please.
Hi, Fábio. Very nice talk. So I have two questions, and maybe they are very simple-minded question, but I was trying to process what you were saying. So the first one is, so if you formally homogenize your inner layer, say in the pipe with the Poiseuille profile, do you get the scaling for Navier friction boundary conditions? Because I mean, you know, if you have very oscillating boundaries and you homogenize them in the right regime, you get Navier. But here I'm thinking of homogenizing the layer, not the wall. Okay, even formally. I mean, have people looked at that, thought of that?
I don't think so. I don't know.
Okay.
I mean, first, I don't know the answer. I don't know. And I also haven't seen any reference concerning Poiseuille flows and homogenization and Navier boundary. But maybe Gabriela knows better, but or Elena. But no, I don't know. I don't know.
Okay, my other question is, you mentioned non-Newtonian fluids and friction scaling, right, for friction laws. I mean, using Komogorov scaling, you get certain friction law. But my question is, what about elastic turbulence for very low Reynolds numbers?
Yeah. So this is we are working on it. That's a work that we never finish. It's been for like 3 years working. But so there's some nice things here going on. So this is the power law, right? Flows. That's very well known. And when n goes to 0, you should have the limit of. So for n lower than 1, you will have what we call the shear thinning flows, right? So so you have drag reducing properties.
Right.
So for a physicist or an engineer, the way they want to reduce some flow is by adding some polymers that you have this shear thinning property. You have less friction. And in the limit that n goes to 0, you would believe that, okay, when n goes to 0, you have the ultimate shear thinning flow, right? But this goes to some limit, some well-posed limit. It goes to 1 over Reynolds 1/2, right? Okay, so you have this limit, and then and there's associated mean velocity profile. Use the same theory here. That is surprisingly a power law scaling with 1/3, the Onsager 1/3, the Komogorov's 1/3. So there's some weird stuff that I haven't, I don't know what's going on. When n goes to 0, the mean velocity profile becomes 1/3 power law, and this becomes 1/2. Now you talk about elastic turbulence. So we work with some elastic models, right? Some UCM upper convective Maxwell models and some other models. And these two elastic models, it's weird that when we send in the limit of the shear thinning limit for elasticity, right? So in the ultimate shear thinning limit, the friction also becomes 1 over Reynolds 1/2. So it's independent of the rheology that you're using to reduce friction. It somehow, both of them, even this is non-elastic, right? This is purely viscous.
Right.
But the purely viscous and the elastic, they have the same friction law at the limit of the ultimate shear thinning. So this, for me, it's completely open. We haven't published it yet. I'm trying still to understand what's going on there. But yeah, so we do have some, we are working on this thing for Odroid B and UCM. We have friction for these guys, this extended friction using this Komogorov's theory. But when n goes to 0 or the elastic time there goes to, when you use the ultimate shear thinning, they both converge to the same law. So yeah, it's weird.
Very interesting. Thank you.
Yeah. No, thank you for the questions.
Are there any more questions, comments? Okay, let's end the speaking again. Thank you, Fábio.
Thank you guys. It's really nice to see you.
And we resume in 1 hour, 10:13. We have a long break here, lunch break for us. See you later.